those projects that John talked about. Barry Fell's going to talk about CLARA, so I'll just let him get set up.
Okay, thank you. This is my clicker. Right, so Barry Fell talking about a fell. Yes, if you believe in nominative determinism, I should know what I'm talking about. Fell being, am I okay? Being standing for free electron laser, and the fell in particular I'm talking about is the CLARA Compact Linear Advanced Research Accelerator, if we're getting our acronyms out the way. So first thing, what is free electron laser? Okay, it's certainly a laser in its monochromatic, and it means single wavelength, and it's coherent. All the light pulses are in step with each other. It's also got a great advantage over standard lasers. It's very tunable, of a wide range of the electromagnetic spectrum, and it's driven by an electron accelerator, as we'll see. It comprises an undulator, a conventional kind of planar undulator, series of blocks of magnets. People from Diamond will be familiar with these kind of things already, through which we send a bunch of relativistic electrons. Okay, and relativistic electrons, when you're in the X-ray sense, you're talking about 1, 2, 3 more GeV. Some of them go up to 17 GeV. So these are extremely energetic electrons. And the undulator array, again, in the X-ray regime, where the most useful science is done, the free electron laser, you're talking about 100 meters plus of undulators. So it's not familiar with people from synchrotron sources. So if people don't know about undulators, so as the electrons pass through, the magnet array causes the electrons to wiggle from side to side, emits a powerfully intense field of X-rays, electromagnetic radiation, strongly emitted in the forward beam direction. In an X-ray fell, it's so intense that the radiation acts on the electrons by the wonderfully termed ponderomotive force, and it forces them to bunch up together with the radiation itself. So the electrons end up forming microbunches that's separated by a radiation wavelength, and that gives you coherence, and that gives you immense power squashed into a very short time frame. It's very different from a typical laser. If you think of a titanium sapphire laser, the wavelength of light that comes out is bound by the atomic lattice, the energy of the electrons in the atomic lattice of titanium sapphire. And that's where you get the free electrons from. They are not bound by an atomic lattice, and then they can be changed to whatever wavelength you desire by simply changing the energy of the electrons. The other plus point is, you'll see it's going through a vacuum. The electrons, free electrons themselves, are the lasing medium. So they won't suffer from a high-power, nonlinear effects, thermal effects that you would get in a conventional laser. Okay, we talked about ultra-relativistic electrons. That seems the only big downside of how you form a free electron laser. One source you might look at is synchrotrons. I talked about GeV. Well, Diamond, if I recall, is 3 GeV. So that sounds like a good set of power to look at, and that the electrons get their energy from ramping up through a handful of cavities. I think it's 6 in Diamond. But so even I talked about them being 100 meters long. That's not consistent with the likes of Diamond, which is about 500 meters in circumference. But let's say you could stretch out a synchrotron. Is it possible to slip in a 100 meters long array and get the sort of what's called saturation lengths that would enable a fell to run? The answer is absolutely not. The timing structure the synchrotron does not allow for the X-ray FEL lasing action. And even if you could micro-bunch them, I believe it's disruptive to the synchrotron, which is trying to be held in equilibrium. Other greater minds than mine have thought about that and not come up with any answers. You can't retrofit them onto synchrotrons as much as you may like to. Right. And the only way you can get an X-ray FEL accelerator, as of today, is looking something like that. You have to line up a huge number of cavities, each one adding more and more energy to the electrons. So if you want GeV, you need thousands of cavity cells. And that inevitably means hundreds of meters, even kilometers of cavities lined up. And the free electron laser, as I said, itself is typically 100 meters. Okay, so electrons go through, wiggle, 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 X-rays out. The electrons are just dumped. They're useless. You can't feed them back, except under special circumstances. But that's mostly, in principle, an X-ray FEL accelerator. Little examples of the cavities. You can have superconducting or normal conducting. Showing you a superconducting example there. Superconducting gives you, you can have much higher pulse rates. For normal conducting, you get a few hundred hertz pulse rates through a machine before you start to melt the cavities and pour in vast amounts of RF power. Because these are superconducting, doesn't require as much RF power. That's the plus point. The negatives are you need a cryogenics plant, which are very expensive and very difficult to implement. But they are implemented. Flash is there as an example. And XFEL, which is, I think, the biggest X-ray FEL, is superconducting. Undulators, fairly standard. So I've given an example of LCLS. The only problem is you need to align 100 meters plus of them more accurately than you would with from a synchrotron undulator, as in towards microns. And I don't think it's feasible to do it with survey networks. I think they rely on beam-based feedback alignment, so it's a sort of dynamic system. Right, okay. I thought people might be dropping off here, so let me enliven you. I like this video. I hijacked it from Daisy and spliced it together. This is, okay, so that laser beam, there's an electron as the red dot from a copper cathode. We're sailing down the cavities, the EM RF pulses there, the EM fields, magnetic electric fields, red and green and blue, faster and faster and faster and faster and faster. I think this runs about a minute, but I think it's a minute worth spend. Dizzying to watch. So you can imagine, for XFEL, you've just gone 2 kilometers. Now we're into the undulator. You see the magnet blocks. Here's the electron bunch being wiggled from side to side. Photon field developed. Very powerful. Now in the next bit, it will show the same. We're zooming in to the electron bunch. A cloud of them. And guess what that's German for. Photons being emitted, and they're now forcing the electrons to dance with them in the same pattern. And so you're seeing this coherent bands, and that can only be nanometers wavelength. So that's a nice little video. I hope I can find my way back to... Right. Okay. So a quick comparison to FELs versus X-ray SR sources. Why are they so valuable? Why do we want to build them? We talked about what they are. So these are the big numbers. Time structures, 1,000 times shorter. You can get femtoseconds instead of picoseconds, and you can't get down on picoseconds of synchrotron. It's entrapped in the geometry of the machine, as I understand it. Energy per pulse, 1,000,000 times more. Right? Monochromatic is 100 times better than, say, a 3% bandpass you'll get off a synchrotron undulator. Each pulse is monochromatic, but it does dance. It can dance around a bit in terms of energy, and I'll come on to that later. They are fully coherent, whereas SR undulate is only part coherent. So that leads you to the big headline graph here. And sure, I thought I had a pointer. Down here, you've got your third generation synchrotrons. I think that's diamond undulate 33. But this is logarithmic. So you're talking, 1 billion times brighter. This is the sort of thing they call, I've seen it classed as disruptive technology. It's almost what synchrotrons were to the X-ray vacuum tubes, generation. It's that level, it's that class. So there's quite a lot of information there. Better maybe just to look at the pros and cons. This was from Jim Clark's slide. So each pulse of light is typically 1 billion times brighter, 1 million times more energy, 1,000 times shorter, coherent and monochromatic, very laser-like. And critically, they enable some experiments that can't be done in any other conceivable way on a synchrotron. And they are tunable and very versatile. Each pulse of light is noisy in intensity from pulse to pulse. It can fluctuate by certainly a few percent, 10%, and in wavelength, similar amount. The costs are similar-ish, depends on the machine. Certainly things like XFEL, the biggest FEL can cost like €1 billion, I think somewhere near that number. And the FELs don't have nearly the same number of beamlines. You're talking half a dozen instead of dozens. So the ugly from that would be, the cost per experiment is even significantly higher. What can we do with a FEL? Well, if you're Dr. Evil, you could try fitting into a very large shark. They are powerful beams. I think he fitted one on the moon, didn't he? But in all seriousness, the US Navy has invested a lot of money in Jefferson Lab over the last decade or so, trying to build a 100-kilowatt free electron laser weapon, a whole accelerator to be fitted on a battleship. More productive things for mankind you could do. And I've only got one example, but there are many, and this is from Jim. So angioreceptor blocker drugs are used for controlling blood pressure, so they stop you constricting the blood vessels. So they were looking at how the drug binded to the cell membrane. It understood that there was a certain mechanism, and they needed to understand at the molecular level. So they ran this experiment on LCLS, and all the theories about what they would look like were wrong. So that leads presumably to a better understanding, shows you how you can create better drugs. The point about this is, this experiment was only possible using the femtosecond pulses from LCLS. No other type of machine can touch this. I believe you need the brilliance and the short time pulse. You can gather up all the crystallographic data by the time it's self-destructed. The power of the beam blows the protein molecules apart. Right. Quick look at X-ray facilities. Still not really onto CLARA yet. But I've talked a lot about them, so there's 3 examples of the big ones. SACLA, Spring 8 Japan, 8GeV machine, normal conducting, but C-band technology. LCLS, I've talked about. Again, normal conducting. XFEL has been alluded to that the UK are collaborating in, I think, to the tune of 30 million. That's a huge machine underground, 3-kilometer span, and down at the very hard X-rays, 0.05 nanometers, if I recall. There's a list of other machines there, more soft X-ray, smaller machines. Okay, so does the UK have any light source ambitions? CLARA we know about. It also has ambition, new light source. I was a member of the team led by Richard Walker that looked in depth at a fully spec'd out concept of what a UK FEL source would look like. The design report was finished 2010. It's a 2.2 GeV machine, superconducting, up to 1 megahertz pulse rate and into the soft X-ray region. Okay, and as you can see, it's a big beast, 700 meters, nearly a kilometer long. Okay, so the timing of that report coincided with the economic crash, and effectively, it was put into cold storage. Not to die, but to wait until an economic spring arose. Whether we're in that yet is another question, not for me. But it's still being considered. Presently, as of 2015, there is a UK FEL strategic review in progress, waiting feedback. In the meantime, CLARA is being funded in phases. You've seen that before, I think, in John's slide. So I thought this would be your first look at it, your second look at it. Electrons generated here in GUN and LINAC 1, and then they're accelerated and manipulated. It goes through the VBC's variable bunch compressor, so they turn the beam around and squash it down to femtoseconds, ready to be fed into the second LINAC 3 and 4, boosted to 250 MeV. Notice I've been talking about GeV, so that's a quarter of a GeV, and that's its sort of final energy. Then into interaction with laser beam. I mentioned about it being noisy, the output of a FEL. If you fire a powerful seed laser down the line of the FEL action, you can quell a lot of that noise. If I'm seeming vague, I'm aware it's an engineering talk. I don't want to try and turn it into an accelerated physics talk because I can't anyway. The FEL output studied out there after about 30 meters of undulators. Note down in the bottom left-hand corner, the blue area, as a picture on the bottom right. Vela is a pre-existing facility, and there might be a tour around there later if you're signed up for it. So there is a facility there that's essentially a high-energy electron gun used for various studies. And initially, CLARA was supposed to run off that or assimilated into it. And Vela's proved so useful that CLARA, we've squeezed enough space so it can run alongside it. So does that mean that what we've seen there is that CLARA, is that a sort of a cut-down version of ambitions, chopped off? You know, that we had this grand X-ray FEL, and what we've got is essentially the 400 million cost of what was the NLS. CLARA is going to be about 1/10 of that. Is that all the money we've got, and that's going to be the UK FEL? No, that's not what CLARA is. So you've seen it. It's 0.2 GeV. It's only 100 meters long. It can never get to X-ray energies. It can't do a lot of useful science in the X-ray energy. It can only it will produce ultraviolet, vacuum ultraviolet range wavelengths, which you do some science in, but not where the great interest is. So what CLARA has been realized as its raison d'etre is a purpose-built, dedicated, flexible test facility for FEL technology and techniques. It will be a precursor to what we hope will be a fully funded X-ray FEL in the near future, something like what you've seen, NLS, but that will depend on the review of where we're going with what the UK wants moving 5 years on. And as I've said, it won't be doing X-ray science itself. So it will be capable of testing a lot of the new promising FEL schemes that are developing almost daily. Both for the UK source, it will inform for the new source, and as part of other international collaborations. It's worth noting that the existing user-dedicated sources, like you saw LCLS and XFEL, are already massively oversubscribed. They don't have time to operate an extensive R&D program to try all these techniques. So that's its USP, unique selling point, and my understanding that's well received around the world. People will be queuing up for that. Swiss FEL have been giving us equipment and advice in return for future time allocation on CLARA. So there are already customers queuing up. So the overall costs, 10% cost of future felt, which is quite reasonable for any kind of R&D enterprise. And the desire is to press ahead quickly so that CLARA can be realistically inform the design of a full UK FEL if possible. Right, I'm running late. And I knew I wouldn't, this is good because I can't explain this anyway. Okay, right. Right. So, yes, two techniques that are like homegrown at Daresbury that are, as I understand it, world-changing would be this high brightness SASE, self-amplification, spontaneous emission. So down here you see, this is what I said, shot to shot, pulse to pulse. You get this wavelength spread. Yes, I'm not going to try and explain how this works. Suffice to say that it's a new technique that will involve us redesigning the undulators planned for CLARA from here to look like this down at the bottom. And you should get this very pronounced, highly monochromatic spike, increase in power intensity in a very defined narrow wavelength. So, right. And another, I'm going to have to move on to CLARA soon. This is mode-locked afterburner. I was a bit disappointed that afterburner didn't turn out to be a big jet engine. As a mechanical engineer, it was not a jet engine. It's just another undulator added onto a load of other undulators. But again, I'm not going to explain it other than this will get you attosecond, not femtosecond, time pulses. And that's going to be, of interest. That's the sort of time light takes to cross an atom of that level. I saw even a paper with yoctoseconds on. I'm sure that excites somebody. That's the next level down. This is for reference. I haven't got time to go into this. All these are CLARA parameters. If you want to look at the slides later, you can. But you see the felt pulse arrival time is 10 femtoseconds. Again, that just indicates that although CLARA doesn't have X-ray capability, everything else it does in its time structures and its infrastructure is compatible with lending it to investigate all the FEL techniques and modes of operation that will be needed. Right. Where will CLARA be built? There, in the old SRS outer electron hall. It's worth pointing out, I've said already, that's where Vela is on there. So, as a token, CLARA is taken seriously. STFC have agreed to fund a rather expensive refurbishment of the SRS outer hall. It will now be called the Electron Hall. This will be massively insulated. And we'll have a temperature stabilization of about, less than a degree, summer, winter. Inside that will be the bunker CLARA, 0.1 degree. And further inside, in specific areas, attempting to get to 0.01 degrees. I'll come on to that later. So that's just an aerial view. CLARA out electron hole fits nicely. CLARA will be built in phases. So here is phase 1, and that's starting in just a few weeks' time. You can see Vela running alongside here. This is existing, and this will be the new setup for CLARA front end, which includes the gun, a cathode chain system, the first linear accelerator up to, it says 50 MeV maximum, and various diagnostics, and just into a dump. That's been funded by STFC, $3.5 million. I said that you need another, that's 10% of about a full CLARA. So, close up, it consists of 3, we're breaking it down into modules. They're assembled and surveyed and tested offline and shipped into the area so to cause minimum disruption in building. This is what's going on right now. John Walmsley showed these slides before, so I won't dwell on it, but there's the 3 of those modules, and that's about what the front end comprises of. First footprints of CLARA. So the start of the year, we moved the shielding around, pulled this back, and did what's called dirty work, as in routed out the floor, ready for the pedestals. So installation ready to go. The Vela CLARA is about 1.5 meters between them. It gives you just enough room to squeeze work here, and there's still enough room to trundle major equipment down this side. Phase 2 will send us out just beyond this slide, actually. Variable bunch compressor, that's part funded. But in order to complete it, we'd need more STF funding. So that sends us out to about 20, 30 meters of our 100 meters. Right, so okay. Nearly done. CLARA engineering challenges. Okay, there are many. One thing mechanical engineers focus on that perhaps our gun is perhaps the best in the world. We've learned from Daisy Pitts, the kind of gun that will go on the XFEL flash. We've added RF probes, done a lot of thermal modeling. Perhaps the biggest challenge in my mind will be vibration temperatures. Reports back from Sackler talking even about pressure changes, atmospheric pressure changes affecting electronics and the timing and control down at this level. Okay, so I'm running out of time, so I will move on. CLARA status, and then a summary. Conceptual design, covered. SwissFEL collaboration, we have 3 Linux and solenoids from them. These are the phases. This is happening now. Talked about it. So we expect first electron spring 2016, and we'll have access to bright short 50 MeV electron bunches. That's been funded, as I said, by STFC. Phase 2A is up to 30 meters out, 150 MeV, and that part funded by STFC procurement starting this year, but it doesn't enable you to finish installation of Phase 2A. And then Phase 2B will be the whole 250 MeV test facility. Okay, not yet funded. CLARA is a clear priority for STFC, and additional funds are being requested from the government in the CSR. In summary, X-ray fells are almost a paradigm shift, big step change in light source users, enabling experiments that previously not possible. So you can imagine there are quite a few scientists queuing up to use these sources, considered a premier X-ray source, but can still be improved significantly with lots of different modes and techniques. But that's the point of CLARA. It will enable you to explore these modes and techniques in a sort of more timely way than you would have on a user facility trying to squeeze different modes in. So CLARA, aiming to improve FEL performance. The emphasis will be on stability synchronization, ultra-short pulse generation, and developing our skills and technology for a future X-ray FEL. CLARA Phase 1 starts installation a few weeks' time, and that's a reiteration of what I said. We are optimistic, and John Walmsley made positive noises that STFC will support for the full funding finishing in 2020. And they've already committed to electron hall refurbishment this year. Excellent. Okay, thank you.
Okay, so in the interest of trying to get us back on schedule, John's fault for a little bit late, not yours, Barry.
I have a convergent thought process with John Walmsley, so...
There you go, there is a tour around to see these facilities, so if you want to sign up for that at the end of the day,